Now we're going to continue explaining rotational dynamics. In this paragraph, we're going to study the moment of inertia. So what is this moment of inertia I, and what importance does this quantity have in rotation? To know its significance, we're going to conduct a small experiment to illustrate that. Consider this object. This system is formed of a rectilinear rod carrying two identical masses at its extremities of 60 grams each. Notice how this system is in equilibrium. We are going to start the experiment by bringing another object and let it fall from a certain height on one of the masses, and let's notice what happens. And in particular, what happens to the rotational speed. Now, I'm going to remove the two masses from their initial positions and bring them closer to the axis of rotation. We're going to throw the same object from the same height towards the same initial position of one of the masses. We notice that the solid is now rotating faster than before, even though the mass of the solid is still the same, since we only changed the positions of the identical masses. So what do we conclude? We conclude that the position of the masses relative to the axis of rotation is of great importance in the rotation of the solid. That's why we have to introduce the quantity which is called the moment of inertia. By definition, the moment of inertia of a particle take this axis of rotation delta, and this is the particle of mass m, that is at a distance d from the axis of rotation. The moment of inertia of this particle of mass m with respect to delta is equal to the mass multiplied by the square of the distance. This distance is the perpendicular distance between the particle of mass m and the axis of rotation delta. So what is the unit of this moment of inertia? M is expressed in kilograms in the SI, and the distance is expressed in meters. And as a result, I is expressed in kilogram times meters squared. Now what about a system of particles? This is delta, which is the axis of rotation. This is particle of mass m1. This is another of mass m2. m1 is at a distance d1 from the axis of rotation, whereas m2 is at a distance d2. So what is the moment of inertia of this system? It is equal to the sum of the moments of inertia of the particles with respect to delta, which is equal to m1 times d1 squared plus m2 times d2 squared, plus the moment of inertia of as much particles as you have. Let's take an application. For example, this is the axis of rotation delta that passes through a point O and is normal to the whiteboard, like this. A particle of mass m1 equals to 10 grams rotates around delta at a distance of 2 centimeters. Another particle is at 4 centimeters from delta and has a mass of m2 equals to 5 grams. So what is the moment of inertia of the system formed of the two particles with respect to delta? The 2 centimeters is the distance d1 of m1, whereas the 4 centimeters is the distance d2 of m2. So by applying the formula, which says that we have to add the moments of inertia of m1 and m2, we write m1 times d1 squared plus m2 times d2 squared. And we substitute the values, converting them into SI units. The answer of this formula is 1.24 times 10 exponent negative 5 kilogram meter squared. So now we have learned the moment of inertia of a particle and that of a system of particles with respect to delta, and we have solved a small application. So what about the moments of inertia of some homogeneous solids? For example, a hoop. The hoop has the shape of a circle, where the mass is distributed on the circle of center O and radius R. This is m, which is the mass of the circle, and delta is here. We want to find the moment of inertia of this circle with respect to this axis of rotation, which is also the axis of this circle. This hoop is a system formed of many small particles of masses m1, m2, m3, and etc. All of the masses are found at equal distances r from O. Then the moment of inertia of this hoop is equal to m1 times the distance between m1 and O, which is r, and then we square it, plus m2 r2 squared plus etc. We notice here that r squared is a common factor. m1 plus m2 plus m3 etc. represents the total mass of the hoop, and therefore I is equal to m r squared. For a hoop with respect to its axis of rotation, this formula is to be memorized. Another example, a hoop whose axis of rotation passes through a point A on its periphery. The hoop has a mass m and a radius r. Similarly, this hoop is formed of many particles of masses m1, m2, m3, etc. But the difference here is that each one has a unique distance from the axis of rotation. Thus, I equals to m1 d1 squared plus m2 d2 squared plus etc. But the square of the distance cannot be taken as a common factor here. And consequently, and after some calculations, I equals to 2m r squared, which is not to be memorized. Now for a disk, which has the shape of a circle, where the mass is uniformly distributed all over its surface. This is, for example, O, which is the center of the disk, and this is the radius R, and the disk has a mass m. The masses of the particles that form the disk are found at different distances from O, where the axis of rotation is found. Then I equals to m1 times d1 squared plus m2 times d2 squared plus etc. We can't find a common factor here. So after some calculation, we get the answer I equals to half m times r squared. This is the moment of inertia of a homogeneous disk whose axis of rotation passes through O and is normal to the disk. This formula is also to be memorized. What if we change the axis of rotation so that it passes through a point A? After some calculation, I equals to 3 over 2 mr squared. For a rod whose axis of rotation passes through its midpoint, I is equal to 1 over 12 ml squared, where L is the length of the rod. What if we change the axis of rotation delta so that it passes by one of its extremities? I is equal to 1 over 3 ml squared, where L is the length of the rod and m is its mass. As an example, consider a rod of length L equals to 30 centimeters and mass 60 grams. On one of its extremities, A, we attach a point mass 40 grams, while on point B, which is at 10 centimeters from O, we attach another point mass 60 grams. The rod can rotate around an axis delta that passes through its midpoint O and is perpendicular to the rod. So let's find the moment of inertia of all of this system with respect to delta. I equals to I of m1 with respect to delta plus I of m2 with respect to delta plus I of the rod with respect to delta. Now, given that the moment of inertia of the rod with respect to a perpendicular axis that passes through its midpoint is one over 12 ml squared, which is not to be memorized, and knowing that for the particles we write m1 times the distance between m1 and delta, which is OA squared, plus m2 times the distance between m2 and delta, which is OB squared. We then replace each quantity by its value. We get 40 times 10 exponent negative 3 times OA, which is the midpoint of the rod, so we write 15 times 10 exponent negative 2 squared plus 60 times 10 exponent negative 3 times 10 exponent negative 2 plus 1 over 12 times 60 times 10 exponent negative 3 times 30 times 10 exponent negative 2 squared. The answer is 1.95 times 10 exponent negative 3 kilogram meter squared. This is the moment of inertia of this system, which is formed of the two particles having the following formula and the rod, which has the following formula.